Carrying capacity is one of the surprising aspects of the universe's fractal pattern. Much in the same way ecosystems have a carrying capacity for the number of organisms it can support, a section of a field also has a carrying capacity. We can demonstrate this in the simulator. By setting the field normalization to 0 and the change in pressure factor to 0, you essentially have a black hole. Energy goes in, but doesn't come out. If we add the change in pressure factor back in, we'll notice it can still maintain its shape, but adding more energy eventually results in a point where it starts to periodically eject energy. This is reminiscent of a lot of things we have observed. The most obvious is that it resembles radiation decay. Radiation decay is described as a random occurrence that, over large time spans and samples, has a predictable cadence. As you go up the periodic table to heavier atoms, the incidence rate increases. Of course, the actual mechanism for radiation is more complicated than simply, it's too dense. But fundamentally, that's the issue. Carrying capacity forms the upper end of the S-curve, which describes a lot of fractal effects. The bottom end of the S-curve is when there's too little. The top end is when there's too much. Incidentally, if we look at a graph for population growth, we see that the top end is not a hard limit and is not stable. It can overshoot by a lot. This is exactly what we see in the simulator. It also models free market prices, among many other things. Likewise, way too much energy growth, just like too much population growth, can result in collapse. If you think about humidity, it also forms an S-curve. But what happens when you hit the top of the curve? Well, water starts to condensate. Interestingly, matter can be described as a condensation of energy. Galaxies and solar systems start from nebulas, aka space clouds. When those get too dense, you start seeing rocks, planets, and stars form. Blackbody radiation is another example of this. Finally, the simulator demonstrates an interesting inversion phenomena when energy displacement is strong, but short range. Decreasing the field normalization rate actually reduces the carrying capacity rather than increasing it. Likewise, increasing the field normalization increases the carrying capacity. This only works up to a certain point. If it's too high, it falls apart again. If we take things the other direction, structures form, but excess energy is ejected in the process. This is reminiscent of an exothermic reaction. In fact, water freezing is exothermic. If we look at this again, you can say that the field normalization rate is the temperature, and when we drop the temperature, we turn water into ice.